Let's jump right into this explainer. Today we're looking at a really fascinating paper from researchers at UC Merced and Tianjin University, titled Single Image Dehazing via Multiscale Convolutional Neural Networks. Basically, we're exploring how these researchers are tackling a massive puzzle, teaching AI to literally see through the fog. Now, single image dehazing has been kind of a holy grail in computer vision for a while. Because think about it, a flat, two-dimensional photograph has absolutely zero depth information. So asking a computer to strip away a thick layer of fog from a static image, that's a huge computational challenge. Let's see how they actually pull it off.
Imagine capturing this gorgeous landscape shot, maybe a sweeping mountain valley, but it's completely ruined by a thick layer of haze. As humans, our brains just naturally get depth, right? We can squint and sort of mentally fill in the shape of the mountain behind the mist, but to a computer, that image is just a flat grid of colored pixels. So how exactly do you teach a machine to peel back a layer that doesn't exist in the code and reveal the vibrant scene hiding underneath?
Well, this perfectly illustrates the goal. We want to transform a deeply fogged, washed-out mess into a crisp, vivid masterpiece. And the core revelation here is that we're not doing this with manual photo editing or traditional pixel tweaking. It's happening through a purely data-driven convolutional neural network. It's essentially mathematical subtraction powered by machine learning, and it's completely changing how computers handle obscured visual data.
Section 1. The foggy photo problem and the math behind haze.
To solve this problem, we've got to understand the math of a hazy day. Think of this foundational computer vision formula a bit like looking through a dirty window. In this equation, I represents the messy, hazy image your camera actually captures. The J is the crystal clear image we actually want to see. And the rest of that formula, that's the physical haze blocking our view. Basically, your camera sees a scene, but the true scene is obscured by scattered atmospheric light that mixes with the landscape before it ever hits your lens.
Now, the absolute make-or-break part of this entire process is figuring out the transmission map, which is that t variable in the equation. This map isolates exactly how much real unscattered light survived the journey through the fog to hit your camera sensor. So, for example, distant mountains have a very low transmission rate because light travels through miles of fog, whereas a tree right in front of you has a high transmission rate. If the computer can nail this map, it can work backward to uncover the true image.
But here's why that's so incredibly difficult. We have our foggy photo, we want our clear scene, and we've got to account for atmospheric light and the transmission map. Because there are multiple mathematical solutions for these variables within a single frame, computer scientists call this a highly ill-posed problem. It's like someone giving you the number 10 and asking, hey, which two numbers did I add together? Could be 5 plus 5, could be 7 plus 3. Without more context, you're just guessing.
Section 2. The limitations of the old ways.
Before modern AI, engineers tried using manual, handcrafted features to guess the transmission map. The dark channel prior was a really popular one. It assumed that in clear images, some pixels naturally act as very dark shadows. But, and this is a fatal flaw, it totally hallucinated. If this old rigid math saw a bright white building or snow, it panicked. It assumed anything bright white just had to be dense fog, and it would completely distort the final image.
To fix this hallucination issue, the researchers threw out those fragile manual assumptions entirely. Instead of strict statistical priors that get confused by white objects, they built a multi-scale convolutional neural network. This new approach is purely data-driven. By analyzing thousands of examples, it learned the actual intrinsic properties of haze directly, which completely bypasses the need for human guesswork.
Section 3. Enter the neural network, coarse to fine refinement.
Let's follow a pixel's journey through this dual network AI. The very first module is the coarse-scale network. Its job is to take a huge step back and look at the big picture. It analyzes the entire image at once to estimate the overall holistic structure of the fog. Fog usually follows a logical gradient, right? It gets thicker in the distance. This coarse network acts like a sketch artist, looking for overarching patterns to draw out the general shape of the haze.
It builds this big picture view through a precise four-stage sequence. First, convolution layers act like a sliding magnifying glass finding hazy textures. Second, max pooling kicks in. Think of this kind of like summarizing a book into bullet points. It shrinks the data down to just the most dominant features. Third, upsampling blows that summarized sketch back up to the original photo's size. And finally, a linear combination neatly blends it all into a rough initial transmission map.
Okay, once we have that rough map, we pass it into the second module, the fine-scale network. If the first network was our sketch artist, this one is the detail-oriented cleanup crew. And you absolutely need this crew. If you only use a rough sketch, your final image ends up with awful blocky artifacts or glowing halos around things like tiny tree branches. The fine-scale network prevents all of that.
It works by taking the original hazy image and stacking it right on top of the rough map. Researchers call this concatenating. By checking local, microscopic details against the big picture at the same time, it irons out wild pixel errors. It encourages neighboring pixels to make logical sense together, smoothing out harsh edges perfectly. The result? A highly polished, incredibly accurate map ready to subtract the fog.
Section 4. Training the AI model and final results. Now, an AI is only as good as its training data, but finding perfectly matched real-world photos, one in thick fog, one crystal clear from the exact same angle, is basically impossible. The wind blows, the lighting changes. So the researchers got incredibly creative. They actually trained this AI to remove outdoor fog by using photos of indoor living rooms. They used the NYU depth dataset, which has pristine indoor images paired with exact laser measurements of depth. They mathematically generated perfect fake fog over these virtual living rooms and forced the network to learn how to perfectly subtract it. By mastering the geometry of depth and haze indoors, the AI could successfully apply those rules to the great outdoors. How cool is that? And the payoff from that clever training is just stunning. Take a look at the older method's output. It's still blurry, low contrast, and really struggles near the tree line. But the convolutional neural network output, it recovers incredibly rich details. We're talking vivid greens, sharp structural lines, and deep shadow information that seemed totally erased by the weather. The clarity is literally night and day. Ultimately, this data-driven dual network approach doesn't just produce cleaner, halo-free images. Because it uses a streamlined neural network instead of complex hand-calculated math, it's significantly faster than the state-of-the-art methods that came before it. And speed matters immensely. It opens the door for real-time video dehazing. Imagine a self-driving car in a sudden rainstorm, or a live security camera cutting through thick morning fog instantly without lagging. That is a massive leap forward.
As we wrap up this explainer, it leaves us with a truly fascinating question to ponder. If we can train a neural network to perfectly calculate and subtract the fog from our photos, recovering perfect data from a single 2D image, what other invisible data is hiding in plain sight in our visual world, just waiting for the right algorithm to uncover it?